Good morning and welcome to the webinar series of TechPassion. The topic of today's webinar is on fasteners, more specifically on bolts. The real objective of what I'm going to present is, can we identify good bolts from bad bolts using some technique? And it turns out that modal analysis is a tool that one can use to tell good bolts from bad bolts given a lot of bolts. So in the next few minutes, I'm going to talk about simulation and experiments that we did on the bolts. So in the case study that I'm going to present, we have picked steel bolts, M10 bolts, and that sets the context for today's presentation. We are going to look at the simulation that was performed on M10 steel bolts. Following this, we are going to look at some experiments that were done on steel bolts, very specifically modal analysis. And we will look at key results, and I'll walk you through some of the results and how we interpret them. And most importantly, can experimental modal analysis serve as a tool to tell good bolts from bad bolts? In other words, we are trying to identify defects, or very broadly, this could be extended to the area of damage detection in structures. So that field is called structural damage detection. So in that area also, this technique of modal analysis can be used to identify defects. Here is an overview of the component that we are studying. It's fairly straightforward. Steel bolt, dimension M10, 150 millimeters in length, and modulus of elasticity is 210 gigapascal, Poisson's ratio 0.3, density of 7,800 kilograms per meter cube, and it's 134 grams in weight. And for modal analysis, one of the things that is important to specify is the boundary condition. It was done using three boundary conditions. And the type of the finite element mesh that was used in modeling uses the elements which are tetrahedral and 10-nodal. This shows the results from the finite element analysis that is performed on the M10 steel bolt. You can think of it as a simple cantilever beam, nothing more complex than that. So if you look at it as a beam, the first three modes are fairly straightforward, and those shapes are what we are looking at in this slide. So the first mode comes at 1582 Hz, second mode at 4375 Hz, and third mode at 8460 Hz. So we first performed the finite element analysis, and there was no way of modeling defects into this unless we get into very detailed material constitutive modeling. So we are looking at it at a very macro scale. We took the board, did three boundary conditions, used 10-nodal tetrahedral elements, and performed modal analysis to extract the first three natural frequencies. And then we go ahead and try to see, okay, from this, if I were to model defect into it, from some macro scale properties such as natural frequencies or damping, can we have a way of modeling defects in the board? So that is one way in which we can think of how this exercise can be used in the context of simulation. But if you look at it in the context of manufacturing, say mass manufacturing of fasteners, it is very well known that during the production process, at several stages, defects could be introduced in bolts, and these could be of various types. And a faulty bolt could be a problem, right? To emphasize the criticality of the application, I would like to give one example from literature, which is when you look at an airline, something like a Boeing 787, there are close to 6 million parts, and out of them, 50% of them are fasteners. So that is the significance of the part that we are staring at here. So if there are defects that are arising in these lots when they are manufactured, this could lead to failure. So it is important to have a way of separating the good bolts from the bad bolts in the manufacturing line. And you need a simple, cost-effective technique that will let you do that. And modal analysis as a technique can go towards that is our discovery, and that's what I'm going to present in the next few slides. So moving on from simulation, we took these bolts, did experimental model analysis on that. The mass of the bolt is mentioned here because its mass in relation to the mass of the sensor is critical when it comes to doing this experiment. So we could be doing this experiment and improve its accuracy even further by using a smaller sensor. But in this case, we use the sensor on this bolt, which is 134 grams in weight. And when this model, if it is translated within the VMAP software, this shows the bolt and 5 locations where the sensor was mounted and measurements were done. So the experimental setup consisted of a 4-channel data acquisition system with a sampling rate of 50 kilosamples per second. And we use a small impact hammer with a force rating of 400 newtons and a frequency range up to 8 kilohertz and a sensitivity of 11.2 millivolts per newton to hit the bolt. And the vibration response is measured in one direction. So we are using a uniaxial sensor of sensitivity 100 millivolts per G, and it's 4 grams in weight. So given these two weights, you can work out what is the mass ratio of the sensor with respect to the component. A quick measurement would give you these two signals. And what we are looking at is the stimulus signal that is measured out of the hammer and the response signal measured from the accelerometer. By doing further analysis of the data and doing some computation, we arrive at the frequency response function. The plot in the red is the magnitude of the frequency response function, and the plot in green is the coherence. Like what you saw 2 slides ago, in the results of the finite element analysis would give you the first 3 modes. Similarly, here, through experiments, we extract the first 3 modes. And this shows the deflection shape corresponding to these modes. And the frequencies that we calculated, 1620 Hz from experiments for the first mode, 4352 Hz for the second mode, 7978 Hz for the third mode. So far we have not addressed the idea of defect. We are only establishing the methodology. So we take a poll, we did simulation on that, then we followed this up with doing an impact testing, and we are looking at these frequencies. Now, the question to ask is, what parameter will you look at to be able to tell the defects, which could really vary depending on the process. But in this case, we are able to identify some parameters which are able to clearly segregate the good and the bad. Even before I get to the concept of defects, I am presenting here the correlation of the mode shape between the simulation and the test. We are looking at the deflection shapes and the corresponding resonant frequency value. In some cases, what we get from experiment is higher than what we get from simulation when you look at only the frequency value. In some other cases, it's the other way around. But what's more important is the modes are clearly separated and the shapes are matching. So to establish the correlation and set it on stone, we need to quantify it, and here we use modal assurance criterion. So there are different curve fitting techniques that you can use to extract the resonant frequencies given the experimental vibration measurement data. And we are using 2 such techniques. One of them is the rational fraction polynomial fitting. And what we are looking at here is the best possible correlations are around 92% for the first mode, 84% for the second resonant frequency, and 83% for the third resonant frequency. Now I come to the real question. Given a structure and say it has defects somewhere, we want to know if there is a way of saying which structure has defects, which one does not have defects. So for that, we need to know what is the parameter that we can use. Even before that, what signature that you would use. So we asked the question of, can we use frequency response measurement as a signature to classify good and bad goals? And we did this, we repeat the experiment for it is statistical. We look at a large lot of goals, and here I am presenting the results from the good and the bad one. So this goal is 212 grams in weight, and experimental setup remains the same. And what we are looking at here is the frequency response function, amplitude and the phase plot. And after doing averaging over the lot of the good and the bad ones, we get this frequency response function, a clear separation between the good and the bad one. It may not look as big as I am saying it, given the scale. But if you look at the actual numbers, both in terms of the frequency value and the damping, the good bolt in this case is separated from the bad bolt by 72 Hz. This is quite significant, and this could be used to automate this in a shop floor setting. So we look another lot, and there again we are able to see a clear separation between the good and the bad, both measured in terms of the frequency value and the damping. So here we are looking at nearly 35 Hz as a difference in the frequency. There is also significant variation in terms of the damping. So we would like to state that FRF can be used as a signature to classify good and the bad goals, and we are able to find a significant change in the resonant frequency and damping in effective goals. But what's more critical in performing these experiments is selection of the sensors and excitation location to make sure that the defect detection process is successful. What I would like to do going forward is pull out the data and show it in VMAP to walk through some of the processes involved in taking the FRF and arriving at the frequency parameters. So I just opened VMAP. So before I I'm going to show data from the experiments that we have done. First, I'm going to show the process involved in taking data from these bones and analyzing them and extracting model parameters. The second demonstration, I'm going to use VMAP's plugin called the Test Data Manager, where you can take data from a battery of tests. This is important in this case because we have lots of bolts which are good, and there is which consists of a mixture of good and a bad one, and we want to overlay all this data and do some analysis and then be able to separate the good and the bad one. So first I'm going to show the process involved in analyzing this. So I've imported the test data now. We already have performed analysis and I have the data stacked up here. But to demonstrate how it is done, just want to show for one resonant frequency. The first mode, it shows the curve fit amplitude and FRF amplitude. Overlap these graphs. We have the resonant frequency and Q factor, and from the Q factor, you can calculate damping. It's for one of the nodes, for another node. So you get a pretty perfect fit of this curve fit fit right in perfectly on top of the measured data. And the reason this is done is once the curve fitting is performed, you get a parameterized function where the parameters are the modal parameters, which are resonance frequency, Q factor, and mode shape. I've shown the extraction of resonance frequency and Q factor. In a short while, I'm going to show the mode shape as well. So this is how it looks, and there are 5 locations where we collect data. This is the first mode, the second mode, and the third mode. So we have done simulation also on these boards. So we want to be sure that the models are correlated between test and simulation. First mode, the first mode, and qualitatively I would say, okay, the nodes and antinodes, they match. Then the second mode on test, second mode on experiment, number of nodes, antinodes, the shapes are matching quite well. And the third mode is almost perfect. This is a qualitative or a visual correlation between the test and the FEM mode shapes for the board. Now let's move on and look at numerical correlation, modular assurance criteria. So I have 94% for the first mode, 89% for the second mode, and 83% for the third mode. Okay. So just to walk through the process again, first we imported the data from the test done on the board. Then I showed for one resonance frequency how do you extract the modal parameters through curve fitting. And following this, we looked at visual correlation between test and final element analysis results. And the last step was to calculate the modal assurance criterion, which tells you the percentage correlation between the test and the FEA for the modes that we are interested in. Now I want to move on to the next demo where we want to take data. What we looked at was one experiment. So now if I want to take say 2 or 3 experiments and compare the data so that when I look at the FRF, I can see if there is a significant separation between the two, or I can perform curve fitting and see if there is a significant difference in the other parameters, say damping, between the test and the FEM. Given that, if there is a significant variation, this could set a test procedure for separating the good parts from the bad parts. So this is VMAP Test Data Manager. So I've just opened VMAP Test Data Manager. Importing the model. We don't have any data here. I want to import the data. So this gives me the mode indicator function. FRF amplitude, FRF. I just want to use the entire view for looking at the FRF alone, the amplitude of the FRF alone. Now this is from one of the tests. Now I'm going to bring data from another test. So there you go. So if I try to resolve this more clearly, This is the data that we have. Very clearly, damping has been introduced, but there is also a shift in the frequency value between here and this one. So 4,620 hertz. If I do curve fitting, I can get the exact value of 4,615 hertz. In this case, we are looking at a peak of 4,572 hertz. So that's nearly 45 hertz shift in frequency. And in addition to that, there is a significant introduction of damping between the two parts. So one of these is a good part, and the defective one we observe there is more damping, very clearly put. So from this, can we arrive at other parameters which show even more separation? That's a question that we would like to leave it open. And to summarize again, with the data manager, what we are able to show is data from one test in comparison to the other test. And here we are looking at frequency response function measured from the one lot of bowls and another lot of bowls. And with that, we are able to separate the good parts from the bad parts. Going back to my slides, in summary, we are able to use modal analysis as a technique to classify boards as an application in manufacturing line. And this is enabled because we are able to identify significant differences between resonance frequency and damping. And of course, what's very important is selection of sensors and excitation location, and that will make sure that the defect detection process is successful, and it is critical for this experiment. So that, with that, I would like to conclude my presentation. In the next few minutes, we can take a few questions before we end the session.